All right, well, thank you everybody for coming. Welcome to Wave Club Seminar. This is a discussion group organized to talk about traveling waves in different species and model systems, humans, animals, all kinds of settings. The four organizers of Wave Club are here on the screen. You can see static pictures of us on the slide, or you can see real live versions of us, Irfan, Uma, Bard, and myself. In our outdated photos here. Our presenter today is Yanliang Shi from Princeton, who's going to be talking about spatial temporal cortical dynamics from columnar on-off dynamics to stochastic traveling waves. I learned a few minutes ago from Yanliang that although he's at Princeton now, he's going to be moving to Tufts University in the sometime very soon to begin his own lab there. So that's exciting, and congratulations on that. Here is Yanliang Shi's biography. He got his PhD from Stony Brook and has been a postdoc at Cold Spring Harbor for a number of years, doing work as a member of now he's been at the Princeton Neuroscience Institute and also the International Brain Lab, collecting data on spatial dynamics and traveling waves during perception, decision-making, and behavior, high-density electrophysiology, and his key contribution is looking at attention and cortical states and how they shape spatial temporal pattern correlations. So for all of these reasons, as you can imagine, well, I'm very happy to have him here because his work really fits Wave Club very well. So looking forward to hearing about it. As a reminder, we record Wave Clubs, including today, and they are posted online in our YouTube channel, where you can see something like 20-something Wave Club recordings over the years, which is really fun to me. And you can also learn about upcoming Wave Club events, not only through our email list, but also Twitter and Blue Sky. You can, Wave Club Seminar is the keyword to search for in both cases. The plan for today is that Yen will present for about 40-45 minutes, and then we'll have some time for Q&A at the end. And the best thing to do is to use the Q&A or chat feature to type your questions into the chat, at least briefly, so that Uma and Irfan and I can stay organized with the Q&A. And then what we'd like to do is bring you on stage at the end to have a conversation. Our upcoming speakers are Roberto Budzinski in July, and then in September, we're skipping August, and then Alexander Opitz is going to give a talk at Wave Club in September. Probably both of those meetings are going to be the first week of September, the first week of those respective months as well. I'm going to stop there because my talking is not what you were here to listen to. Yanliang, thank you so much for coming, and I'll let you share your screen and take it from here.
Great. Thank you very much for the introduction. Yeah, it's my great pleasure to present my work on spatial temporal cortical dynamics and the relation to traveling wave. Let me share my screen. So
one day somebody should give a Wave Club talk without sharing their screen, just through using their hands to show waves. But today's not that day. All right.
Can you see my slides now?
Yeah, it looks great. Wait, I'll let you take it away. I'll be quiet.
Okay. Oh, so thank you again for coming to my talk today. So it's my great pleasure to present my work on spatial temporal cortical dynamics. So I will show how the concept of columnar on-off dynamics can be linked to traveling waves on primate cortex. So first of all, I will introduce a concept of cortical states, which characterize the operating regime of cortical dynamics. Then I will talk about how the models columnar on-off dynamics can account for the spatial structure, can account for the temporal structure of fluctuation at the local columnar scale. And then I will introduce a model of interacting cortical column, which account for the spatial structure of fluctuation in cortical dynamics on the cortical surface. And finally, I will show that all of the dynamics can have interesting connection to the traveling wave dynamics across cortical areas. First, let's start with cortical states. So as we know, there's endogenous fluctuations in cortex. So cortical dynamics is not only driven by intrinsic dynamics, but also modulated by external input and also neuromodulation effects. For example, acetylcholine signal from basal forebrain modulate cortical dynamics during different brain states from deep sleep to arousal states. And in the during the the deep sleep states, there's a synchronous cortical states where activities uh, uh, of neurons are highly synchronized, fluctuation between high activity state to complete silent states. During arousal states, there's called desynchronized state, whereas activity of cortical neurons are very desynchronized, and there's very small average correlation between neurons. However, the synchronized state and the desynchronized state are only two extreme cases of internal cortical states. There are a lot of intermediate state between these two extreme cases. So during intermediate states, there's also other type of fluctuation where fire rate can be fluctuated between high activity state to low activity states. And how to characterize so the different cortical states during different uh, behavior such as sleep and arousal. So we can use neural correlation to characterize those cortical states. So namely, during synchronous state, if we measure the pairwise neural correlation between neurons, we find that overall the average neural correlation tend to be very high. Now, while during the synchronous state, the average correlation is very close to zero, and the positive and negative correlation pairs cancel each other. So it turns out that the noise correlation can be used to characterize the correlated neural correlations. And it is defined as a Pearson correlation coefficients between spike count of trials with same stimulus or input. And we find that as that the noise correlation not only affected by the global cortical fluctuation, but also modulated by different behavior states, such as spatial attention. For example, during this behavior spatial attention task, where monkey are trained to fix their eyes into a center screen while pay attention to different spatial location, where one of the stimulus will treat orientation, and by pay attention to a particular locations, mouse can easily detect. Sorry, the monkey can easily detect change of orientation in one of the spatial location. And if we measure neural activity in the visual cortical area, it has been shown that noise correlation tend to decrease during attention states compared to control states. And overall, if you use a utility to sample population neurons occupy in the different cortical column, you can see overall the correlation decrease as a function of the distance. And along the distance, noise correlation tend to decrease during attention states. On the other hand, if you use another device, a linear array probe to simultaneously sample population neurons within local cortical columns, it has been found that the effect of spatial attention is uh, much smaller compared to the measurement using uterary, and the average magnitude of neural correlation within local cortical column tend to be much larger than the neural correlation across cortical columns. Apart from the spatial structure of a neural correlation that are driven by cortical fluctuation, there's also interesting temporal dynamics of cortical fluctuation. So the recent study has shown that if we use a linear probe that simultaneously measure neurons within single cortical column across different cortical layers, as there's bistable fluctuation or fire rate from high activity state called on state to low activity state called off states. And the time scale for this synchronous fluctuation is around about 100 millisecond, which is much longer than the typical time constant of single neuron dynamics. So the question for us is that how to account for the spatial pattern of cortical fluctuation measured by linear array probe turned on-off dynamics, and also how to account for the spatial structure of cortical dynamics reflect in spatial structure of neural correlation that are measured by utility probe, where people have shown that the neural correlation decay as a function of separation between two columns. Uh, So previously, a lot of computation models have been proposed to account for the spatial temporal structure of cortical fluctuations, but none of them can fully account for both the spatial and temporal domain of the structure of cortical fluctuation. So one classical model for cortical fluctuation is the so-called EI balanced neural network models. In this case, it's a strong interaction between E and I population, creating intrinsic fluctuation. However, in this case, the input from E population, I population cancel each other. On average, there's very small mean neural correlations in the population dynamics. And also in this model, the connection between neurons are completely random. There are no internal spatial structure in the neural fluctuations. To account for the non-trivial spatial structure of neural correlation, another balanced network model was introduced. In this EI balanced network model, the connection probability between E populations is a function of distance between neurons. This model can introduce spatial structure of neural correlations, and in this case, the chaotic dynamics from instability can generate intrinsic fluctuation. But the problem is that the fluctuation dynamics are very fast, much faster than the time scale of the observed, which is about 100 milliseconds. To account for the time process structure of a neural fluctuation, so people introduce a adaptation variable to the neural dynamics. In those kinds of models, there's a bicycle dynamics can also generate a long time scale for fluctuation. However, those kind of models fail to account for spatial structure of neural fluctuation. To overcome those limitations of previous models, I introduced an interaction cortical column model, which account for the both spatial and temporal structure of neurodynamics. So for first, let me introduce this model at a local columnar scales. So to account for the temporal fluctuation dynamics at the local cortical columns, we need to account for the anatomical structure of a cortex. So in primate cortex, the neuron, the dense connect form a local cortical column, and then there's horizontal connection between columns for form a cortical surface. To account for the synchronous neural fluctuations in a local cortical columns, I introduced a very simple dynamic system model with two dynamic variables. One account for the population fire rates across for the neuron across all layers. Another is a adaptation variable that provide negative feedback to the system. And by tuning the parameter of the system, this model can generate interesting population dynamics, including on-off fluctuations and also oscillation or other states. So mathematical this model contains a fire rate variable and adaptation variables. So there's intrinsic external noise assigned to the adaptation variable, and combined with the external input to the fire rate variable, this model can generate on-off fluctuation between on and off states. Additionally, if you increase external input to the dynamical system model, which mimics the attention input, so you can change the knock-line of the system such that the transition probability between an on and off state can also change. As shown in this plot, when you increase attention input, the average duration of all on states increase and duration for off states decrease. And this model can account for the observed spike count noise correlation observed in local column. Basically, we assume that all the neurons that in a single cortical column share the same on-off phase generated by this dynamical system model. In addition, each neuron has its own fire rate during on states and off states. So during on state, the fire rates tend to higher and the off state fire rate tend to lower. And then the Poisson process generate a spike count, but based on the fire rate at the on and off states. For example, let's look at those two neurons that are sampled in a in the same cortical columns, and we can check the spike count across different channels for those neurons. And you can see that even with the same shared on-off phase, the different fire rates during on and off state can generate different magnitude of fluctuations across channels, reflect in noise correlation amplitude. So mathematically, we can compute the Pearson coefficients of spike count in this equation, which include two parts. So the first part is account for the fire rate the difference between on and off states, and another part, which is a function of alpha 1, alpha 2, is the part that generated from the intrinsic dynamics of all fluctuations, and this model is able to account for the change of noise correlation during attention. So basically, the model predicts that during attention, the pair of neurons that has a bigger change in of the on fire rate difference tend to have a bigger change in noise correlation, and the pair that has a small magnitude in the change of on fire rate difference has a small change of noise correlation. And moreover, there's continuous spectrums of neural pairs with the different magnitude of change of fire rate, the difference during attention, and the model can account for the change of noise correlation in all those cases. So far, I've shown that as a computational model of a local cortical column can account for the temporal structure of all of the dynamics, and also account for the effect of spatial tension on the transition probability. Next, I will introduce a network model of interacting columns. It generalizes the idea of local columnar on dynamics. Because if we use a utility to sample neural population across cortical columns, we see there's strong correlation, which is a function of separation between two columns. So to account for that, we have to introduce a networked model of interacting columns where each unit represents a single column, cortical column dynamics, which is described by the 2D dynamical system equations that I mentioned before. In addition, there's horizontal interaction between nearby columns. So I introduce the non-local horizontal connectivity between nearby columns, which generate a network model of interacting cortical columns. Mathematically, I can use a neural field equation to account for the both the local dynamics within a single cortical column, but also the spatial structure of dynamics across cortical columns. And basically, numerical simulation of this spatial neural network model can generate a spatial structure of neural correlation as a function of lattice separation between two columns from simulations. And because in this case, at each cortical column, the neural dynamics fluctuate between two states, on state, off states. In this case, I can use simplified the binary units model to derive an analytic equation for the noise correlation structure. But basically, in this simplified model, each unit has a binary state transition between on and off states, and the alpha 1 alpha to describe the intrinsic transition probability between on and over states. And because there's horizontal interaction between nearby colons, the transition probability is also modulated by the interaction between nearby colons. So here you can see the transition probability is also depends on beta s plus minus, whereas s plus minus is the states of nearby cortical colons, and the beta is the interaction strength of the nearby colons. And using mathematical equation, I can derive an analytical equation for the noise correlation. And the equation of noise correlation show two paths, where the first path, a function which is a function of alpha 1, alpha 2, describe the single colon noise correlation, uh, which mainly driven by intrinsic dynamics at the local collinear scales. But in addition, there's another term which described by the effect of spatial interaction. And it describes the fact that the noise correlation decay exponentially as a function of a separation between two colons, and the speed of the decrease of noise correlation is described by this correlation strength L. You can see L is the magnitude of L is directly affected by the interaction strength between nearby cortical colons. Additionally, we find that if we increase the attentional input to local neural population in this neural network model, the effective interaction strength, the beta variable, decrease monotonically as a function of attention input, which account for the reduction of noise correlation on the attention effects. Well, basically, if during attention the correlation length decrease, you will see overall decrease or magnitude of noise correlation across different lateral separations. On the other hand, if attention, if the correlation length increase during attention, then you will see the increase of change of noise correlation on the attention condition. So in summary, that's a network model of interaction colon can account for the change of noise correlation on the spatial attention. But basically, by increase attention input to the local neural populations, we have effectively reduction of horizontal interaction strength between nearby colons, which result in the reduction of correlation length, and which account for the change of noise correlation at the different lateral separation. Namely, if we use a linear array probe to sample neural population within single cortical colons, you can see the change of noise correlation is very, very small. However, if we use a utility probe which samples the neural population across colon with large lateral separation, you can see the overall change of noise correlation is very large. So which account for the distinct observation of noise correlation changing effects on the spatial attention. So far, I've shown that a network model of interaction colon can account for the both spatial temporal structure of noise correlation and account for the effect during spatial attention. So in addition, this model predicts that on-off dynamics propagate across cortical surface across colons, which then maybe generate a statistical traveling wave dynamics. So we are interested to direct test the signature of traveling wave dynamics from the ether recording in primates. So here, the previous simulation in this model shows that the on-off dynamics kind of fluctuates across cortical colons in a spatial orderly pattern. So you can see the local traveling wave patterns in single cortical area. However, previously, if we use a linear array probe, we can only measure the population neural dynamics within local colon, fail to detect the traveling wave patterns across colons. If we use the utility array, which samples multiple colons, but for each probe in the utility can only sample single channels, which also fail to detect the population dynamics within local cortical colons and how they coordinate across colons. So To overcome this challenge, I collaborated with Xiaomo Chen at UC Davis and Thierry Moore's lab at Stanford, where they use a linear array probe to simultaneously measure um, neural population dynamics across different cortical columns. So within single probe, because in the primate cortex, the FE, a frontal eye field, is curved. So even with a single linear array penetration, you are able to simultaneously sample uh, two cortical columns simultaneously, and you can use a reset field shape to cluster neurons in different cortical columns. First, we try to use a hidden macro model to fit off the dynamics of the channel of the all neurons recorded in a single linear array probe. We find that indeed neurons in different columns tend to have a more correlated dynamics within local column instead of synchronized across all channels. As you can see, you can see the population dynamics at a single child level kind of synchronized within itself in a single column instead of cross column. Therefore, we find that the of the dynamics fitting by fitting macro model prefer the separate all fluctuation for each cortical column instead of synchronized fluctuation across all columns. And then after identify the local all of the dynamics for each cortical column, we're interested to know the communication of those of the dynamics across columns. So there's two hypotheses. The first hypothesis, the random wave hypothesis, in this hypothesis, there's no spatial correlation between the all of fluctuation and the local columnar scale. So if you compute the uh, average pairwise correlation of all of phase as a function of a cortical distance between columns, there's no spatial dependence. On the other hand, if there's a local, if there's stochastic wave dynamics that are traveling across columns, then there's a spatial dependence on the correlation of all phase across columns. So we use those data across column to infer the pairwise correlation of all phase across columns. And indeed, we find that there's strong correlation between the all of phase and the separation between two cortical columns inferred from intercolumnar reset field correlations. Furthermore, we want to infer the traveling speed of those dynamics across cortical columns. For that purpose, we leverage the strong correspondence between the LFP signal and all phases. Because at a single child level, we find that there are strong correlation between the local field potential signal and the phase of local field potential to the phase of all of the dynamics at a single child level inferred from spiking activity. So if we align the local field potential signal and its phase to the time when the on-off transition happen, we can see there's a big difference in terms of magnitude of LP and also the phase of LP when the transition happen from on to off phase and also off to on phase. But because that is strong correspondence between LVP and on-off dynamics, we can infer the potential traveling speed of all of wave dynamics from LVP signal. Indeed, if we from our single electro recording, we find neurons that located in different cortical column has a distinct LFP wave phase. Showing this plot, you can see that channels in neurons cluster in single cortical column tend to have shared LVP phase, while neuron has in separate column tend to have a bigger difference of LVP phase. Indeed, on average, for neuron paths across column, we can see on average is a larger phase difference compared to neuron paths within single cortical columns. And furthermore, we can find as there's strong correlation between the lag of LFP phase for neuron paths across colons and also the physical distance difference of two cortical columns infer from channel distance or from the LFP correlations. From this relationship, we can infer the traveling wave speed of all of the dynamics. So in summary, here I show that a local of the dynamics can account for the local cortical states and attention modulation effects during spatial attention task. And a network model of cortical of dynamics can account for spatial temporal cortical dynamics. And finally, all of dynamics are related to traveling wave patterns, which can be indirectly inferred from the correspondence between LP and the on-off phase. So finally, I will thank Tatiana Angle Lab and our collaborator across the different institutions. And finally, I will to announce that I will join the Department of Neuroscience at the Tufts University as an assistant professor in December this year. So there will be several positions of a postdoc PhD position available. Please feel free to contact me. So thank you again for your attention.
Very cool. Thank you, Yanliang. Yes, claps.
So thank you.
We have time for some questions now.
I have a question.
Please.
Oh, I don't know how my video came. Yeah, in those pictures that you show of you have all these spike rasters, okay?
Yes.
And you can show me an example, I guess, where you've distinguished between up and down states somehow. And
Yeah,
I'm
yes.
okay. So, all right. So in that first group, how do you know when something's in an up or down state? What is the criteria?
Oh, we use a hidden Markov model to infer the possible states of on state, off state. We use a hidden Markov model with a different number state to test which model best captures the spiking pattern of data. We find that in our data, in the most of the case, the two-phase hidden Markov model can best capture the fluctuation pattern of spiking data. So we call those data on state and off states.
So like for example, like these guys, there's a few yellow guys there that are mixed in with the blue. Um, um,
Oh,
or right. Here, I just right there. Like,
okay.
how did you know that those guys were up and the other guys were down?
Yeah. I totally agree. It's not a there's no ground truth. We can use a model in inference procedure to obtain the
I,
maximum likelihood of all states.
okay.
At a single child level, there may be some fluctuations that not looks very nice, but overall across all childs, across all session, all animal, we find still the two-phase model capture the overall. A lot of fluctuation patterns in the
So
spiking
it's not
data.
obvious by looking. You really have to do some very
Yes.
okay.
Do you have other questions? Please ask.
No, that's good for me.
Okay, so thank you.
We do have a question that just came into the chat. Ganendra, I'll put you up on stage to ask yourself.
Can you hear me?
Yeah, I can hear you. So,
Yeah, sorry, there is a background noise. Actually, I was traveling. So what you showed was quite interesting. I was wondering again what Bard asked, that is it really the switching state you observe? And also, along with the switching states, do you also observe these, let's say, traveling of these spontaneous patterns across your cortical brain?
so the question is, can I observe the switching of on phase across colons? Is that right?
Yes, exactly. You showed you have, let's say, up-down state dynamics, which is changing, right? So do you
Ye-
also observe these traveling patterns apart from these switching states? Like, how do you really define these as, let's say, spontaneous traveling patterns?
Oh, I see, I see. Yeah, I have to say yes. If we only record using linear array probe at the local collinear scales, we cannot directly infer that traveling wave pattern. However, in a FE in a recording in FEF, um, where the so because of the geometry of a prefrontal cortex, even with a single linear array probe, you can penetrate different colons. And if you those colons are separate by distance, and you can use a receiver field correlation to infer the spatial separation between the two colons. And then for different recording, you have a different pair of colon with the different spatial separation, and then you can say is there strong correlation between the phase or the difference of all states and there's spatial separation. And as there from that data, I can infer the possible traveling wave pattern of all dynamics across colon. For example, if we look at a single child data, the record in a single probe, you can see this. This spiking pattern, you can easily say that at a single child level, population dynamics are more synchronized within local colon instead of across colon. Then we can use a hidden Markov model to fit off transition of two colons separately, and then you can see the all of transition probability kind of does not synchronize across colon. So there are actually the phase mismatch between two colons. And then we can use a correlation between the phase mismatch and the spatial separation between two colons to infer the possible traveling wave patterns.
Is the switching happening at each of the columns or on an ensemble of columns?
Uh, at each recording, we can at the most test two colon or three colons because we only have a single linear array probe. But if we have use other type of probe that can simultaneously record more colons, then we can have a better understanding of traveling wave patterns. Current data we only have those single array recording. But in the future, I'm very interested to see how this pattern can be inferred from multi linear array recordings.
Okay, this last one I had. In one of the slides, you mentioned meta stability, where you showed across population you have a quick transition, and then you have the dynamics which is quite stable for some duration, right? And attention part, where you had attention without attention. So could you explain like how do you got this, let's say this activity where you have fast right and then it was being maintained for some duration? I think in earlier slides, 7 or 8, I think.
Uh, Let me try to find the slides you mentioned. Do you mean those slides
Yeah,
like
exactly. This one. Yeah. So in the attention, like what do you mean by this? Let's say the
yes,
activity goes
yes,
up and then it is. Yeah.
yes, in terms of mathematical equation, so it's very simple. You can increase the transitional transit input current to the finite very variable, and then because of interaction of nearby cortical colons, this attention can not only affect the local transition probability at the local colon scale, but also affect the interaction between nearby colons. At the local colon scale, if you increase attention input in this equation, you basically shift the null clan of this equation. Basically, you can see like if you increase attention input, there's a potential fixed point change. So one fixed point becomes more stable. So the transition probability to the on states will increase, and then the transition probability from on to off will decrease, which happen in local populations. That's account for the attentional effect at the local corner scale.
All right. Okay. I mean, I was just confused, but yeah, it is depending on the applied current. Okay. Thank you so
Yeah,
much.
yeah, yeah,
Interesting.
yes.
Yeah. Thank you.
I had another question comment.
Sure, sure.
So I'm recalling back in 2000 or mid 2000s, 2007 maybe, out of Ken Harris's group, I think they showed that in this is in rat
Uh-huh.
that rat, I think both awake and anesthetized rats, um, that these cortical up and down states did propagate as traveling waves. And I'm wondering how this is what is, I guess, different from this than from what those guys did back then.
I see, I see. I feel in general in monkey we find a more spatial structure over noise correlation compared to
Yeah, they
mice.
didn't look at noise correlation at all. They were just looking at sequential activation of neurons following these up and down states. That's all. I
I
was
see,
just
I
curious.
see.
If how,
Yeah, in general, I feel the correlated cortical fluctuation is more pronounced in monkey compared to mice. And currently, we haven't applied this hidden Markov approach to infer on-off dynamics in mice, but there can be difference between mice and the monkey, I feel. At least for all the primate data I checked so far, we find a very strong evidence for on-off dynamics across a different cortical area from a sensory area like a visual cortex to prefrontal cortex. So it's kind of very universally true in at least in primate cortex. For mice, there can be more complicated because because of the and also because of an anatomic connectivity structure in mice can be different from monkey. Um,
one
yeah, please. Do you have other comments?
oh
There's a comment from Lyle. I can have you
yeah,
unmute.
Lyle's pointing out that it's across lamina and not across cortex. Okay. I thought it was across cortex, but okay.
Oh, yeah. Here's the recording. So it's in the cortex, but across different layer from superficial layer to deep layer. The total length of a linear probe is about 2 million meters. So it's able to sample neural population in all cortical layers, but not able to test other brain area beyond the cortex.
Oh, why do you put the noise on the adaptation?
Yeah, I actually don't know deeply as a reason because you can also use a linear transformation to translate noise in the adaptation variable to the fire rate variable. It also works, but yeah, I don't know the deeper reason behind that. But do you have any comments on that? Like from the equation, you can yeah, if you shift the noise from the U variable to a V variable, you can also generate a stable by stable dynamics from on between switching between on and off. I guess yeah. I guess you can also you can also use a chain of variable to switch the noise from one equation to another equation. I guess, but maybe they operate at a different time scales.
Any other questions? Hey, Lyle.
I had a quick question, if that's all right.
Yeah, go ahead.
Hello.
Great. First of all, great talk. That was
Thank
really
you.
interesting. Yeah. So, what do you think? So, you have a model which accounts for the noise correlations in the data and the changes with attention.
Yeah.
Um, and then you're expanding it across multiple columns. What do you think the functional role of the wave is in this case? Like, do you think that the on-off dynamics just have to happen to propagate across the cortex because of the recurrent connectivity, or do you think that they have a specific functional role?
There's some evidence for the potential function role for the wave dynamics. If you measure the task performance during spatial attention task in different phase, people have shown that during all phase you have a higher task performance compared to all phase. But we don't know if it's causal role for the all the dynamics or the traveling wave patterns. I do say that there's multiple study on traveling wave, including study in your lab that has shown that there's a correlation between task performance and the different phase of wave dynamics. But still, yeah, it's very complicated problem. We still don't have a good answer for that. There can be some you can think as a local modulation wave pattern is a link to a local neuromodulation effect from basal forebrain, and you can see it's those neuromodulation as a signal to guide the task performance or like for local control over or to the local competition capacity in local neurons. So maybe link to the overall traveling wave pattern because we do find in our equation that those neuromodulation effect can dramatically change the possible pattern of wave dynamics. So maybe some correlation. Yeah, but we don't know the strong evidence for that.
That's great. I think it's just interesting to as we're having these discussions to think about what the specific role of the spatiotemporal organization is, because that helps to highlight, as we're starting to see that the activity dynamics that were once recorded at a single point in the cortex, now we're recording across multiple points in a cortical region, seeing that there's spatiotemporal organization, bringing the studies to the next level, it allows us to say, well, what is exactly that spatiotemporal organization doing? I think that's an important question. I think it's interesting. I think that there's lots of interesting connections between the results you have here. So nice.
So thank you again.
Yeah.
It's amazing how many different ways there are that traveling waves manifest, and different parts of the brain showing them in different ways, with different kinds of mechanisms. Anyway, I really enjoy this.
Thank you.
Any other questions?
There's an additional comment from Gnendra. I believe Lyle, switching dynamics could be for memory and traveling waves for computation or coordination across the cortex. Again, just a hypothesis. I don't know if you want to discuss more, but if you do, feel free to come up and chat.
Yeah, I think yeah, the cortical traveling wave can be used as for communication between different cortical areas. For that purpose, we can estimate from using information theory to estimate the information transfer at a different phase of wave across the different cortical area as well. Yeah, it will be interesting test in the future. We are collaborating with Xiaomo Chen Lab at the UC Davis. She has also planned to doing a electro recording of the monkey brain, and for that data we can maybe infer the traveling wave patterns across different brain area during spontaneous activity, but also during a task, and then we can infer how the communication information is correlated with the traveling wave patterns.
Very cool.
Cool. All right, should we wrap up?
Okay,
All right, well, Yanliang, thanks again.
so thank you.
And just as a reminder, Wave Club's our talks are posted on YouTube if you want to go back and check things out. I think that's it, and we'll see you again next month. Take care, everybody. And we're always looking for more speakers for Wave Club. So if people are doing relevant work or know of people doing relevant work, feel free to reach out to me, Bard, Uma, or Irfan.
Thank you.
Right.
Thank you.
Have a great day,
Bye-bye.
everybody. Take care. Thanks again, Yanling.